November 7, 1943. Karpik airfield, northern France. The brutal headwinds over the English Channel had consumed fuel at an alarming rate. Second Lieutenant William E. Roach of the 358th Fighter Squadron watched his gauges drop toward empty as his Pratt and Whitney R-2800 double Wasp engine began to sputter. Below him stretched occupied France, a patchwork of fields where one wrong decision meant capture or death. He spotted an airfield. The grass runway looked remarkably similar to Allied bases he knew. Roach committed to his approach. The massive Republic P-47D Thunderbolt touched down smoothly. He followed a ground vehicle to a parking area, shut down his engine, and only then noticed the Balkenkreuz on nearby aircraft. The Germans he had been fighting minutes earlier now surrounded his cockpit with rifles drawn. Lieutenant Roach's war as a combat pilot was over. He would spend the remainder of the conflict at Stalag Luft 1. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But what German engineers were about to discover when they examined his aircraft would fundamentally alter their understanding of American industrial capacity in ways that went far beyond tactical aviation. The engine bolted to the front of Roach's Thunderbolt represented something German engineers had been told was impossible. A production radial engine delivering 2,800 horsepower with absolute reliability, manufactured not in dozens or hundreds, but in tens of thousands. Over the following months, as German engineers systematically disassembled, measured, and tested the Pratt and Whitney R-2800, they would confront an uncomfortable truth that extended far beyond aviation. Germany had not simply fallen behind in engine technology. They had been competing in an entirely different category of industrial warfare, one where American factories treated advanced metallurgy, precision manufacturing, and quality control as standard practice rather than aspirational goals constrained by material shortages. The story of German engineers examining captured American aircraft engines reveals how overwhelming material superiority, when properly applied to military aviation, could render tactical excellence and engineering cleverness increasingly insufficient to change the war's outcome. The R-2800 would teach German engineers lessons they desperately needed but ultimately could never apply. Their nation lacked the aluminum, the strategic alloys, the machine tools, the skilled workforce, and most critically, the time to implement what American factories produced as routine equipment. The Luftwaffe had been fighting Republic P-47 Thunderbolts since April of 1943, when the 4th Fighter Group first escorted B-17 bombers into hostile airspace over occupied Europe. Initial impressions from German combat reports reflected a mixture of contempt and confusion. German pilots, accustomed to the nimble Focke-Wulf FW-190 and Messerschmitt Bf-109, found the American fighter absurdly large, sluggish at low altitudes, and apparently designed by engineers who had never considered the requirements of aerial combat as the Luftwaffe understood them. Combat reports from German fighter units throughout the spring and summer of 1943 consistently noted the P-47's poor rate of climb below 15,000 feet, its ponderous handling at lower altitudes, and what they perceived as American pilot reluctance to engage in traditional turning dogfights. The initial assessment among experienced Luftwaffe pilots was that the Thunderbolt represented an inferior design that could be outmaneuvered at medium altitudes where most combat occurred. But other details in those same combat reports hinted at something more troubling. Pilots described how Thunderbolts that chose to disengage from combat could not be caught once they entered a dive. They mentioned 8 heavy machine guns that fired with devastating effect. They noted armor protection that seemed impervious to standard 7.92mm rounds and often resisted even 20mm cannon fire. Most disturbingly, they reported that even badly damaged Thunderbolts continued flying, limping back to England with battle damage that would have destroyed any German fighter. When Lieutenant Roach's intact Thunderbolt rolled to a stop at Karpik, the Luftwaffe finally had the opportunity to examine in detail not just the aircraft, but the engineering philosophy that had created it. Local Luftwaffe personnel immediately recognized the intelligence value. Within hours, the aircraft was surrounded by armed guards. American markings were painted over with German Balkenkreuz. Bright yellow identification paint was applied to undersurfaces and tail surfaces, the standard RLM-04 yellow used to prevent friendly fire from German anti-aircraft gunners. Arrangements were made to transfer the aircraft to Rechlin, the Luftwaffe's premier testing facility located approximately 100 kilometers northwest of Berlin. The aircraft received the designation T9 plus FK, the coding used by the Circus Rosarius Evaluation Unit. But before any flight testing could begin, German engineers needed to understand what they were dealing with. The engine became the primary focus of initial examination. Hans-Werner Lerche, the principal test pilot and chief engineer at Erprobungsstelle Rechlin, approached the Thunderbolt with professional curiosity. His first impression, documented in his logbook and later published in his memoirs, reflected surprise not at the cockpit's complexity, though that was considerable, but at the sheer physical scale of what sat in front of the firewall. The Pratt and Whitney R-2800 double Wasp consisted of 18 cylinders, arranged in 2 rows of 9 cylinders, each around a central crankshaft. Total displacement measured 2,804.5 cubic inches, equivalent to 45.958 litres. For direct comparison, the BMW 801D, Germany's finest and most powerful radial engine in operational service, and the power plant of the Focke-Wulf 190, displaced 2,560 cubic inches, or 41.88 litres. The American engine was larger, but displacement alone didn't explain what German engineers discovered when they began detailed examination. The R-2800 incorporated forged aluminum alloy pistons of a quality German metallurgists examined with professional envy. Sodium-cooled exhaust valves handled extreme temperatures that would destroy conventional designs. The crankshaft was forged from high-grade steel alloy that German engineers recognized as superior to anything available in German production by late 1943. Every component showed evidence of precision manufacturing to tolerances tighter than German wartime production could consistently achieve. Surface finishes were uniformly smooth across all parts. The magnetos used materials that were increasingly scarce in Germany. The spark plugs incorporated high-grade ceramics of superior quality to German equivalents. The fuel injection system operated with precision that German engineers associated with laboratory equipment rather than combat aircraft, expected to function reliably under harsh conditions. Most tellingly, the entire engine showed no signs of material substitution or quality compromises forced by resource limitations. German engineers began their systematic evaluation by carefully documenting every dimension, every material, every manufacturing technique they could observe. The engine was photographed from multiple angles. Major components were removed, measured with precision instruments, weighed individually, and analyzed for material composition through metallurgical testing. The inspection team consisted of experienced German aviation engineers who understood radial engine design principles thoroughly, having worked on the BMW 801 and earlier German radial engines. What they discovered challenged fundamental assumptions about what was possible in production engine manufacturing. The quality of American materials astounded the German inspection team. The aluminum alloys used throughout the engine incorporated copper, magnesium, and other strategic materials in proportions that optimized strength and heat resistance without compromise. Germany, by late 1943, faced severe shortages of these same strategic materials, forcing the use of substitute alloys with inferior properties. The steel used in the crankshaft, connecting rods, and other highly stressed components showed consistent grain structure and material properties, indicating careful quality control during forging and heat treatment processes. German wartime steel production had become increasingly inconsistent as high-quality coking coal grew scarce and production facilities suffered damage from Allied bombing. The American engine showed no evidence of such compromises. The cylinders themselves revealed sophisticated manufacturing. Each cylinder barrel was forged from steel alloy, then machined to precise dimensions with a nitrided surface treatment that provided extreme hardness and wear resistance. Aluminum alloy cylinder heads bolted to each barrel incorporated precision cast cooling fins that maximized heat dissipation. The valve seats were hardened to withstand the pounding of sodium-cooled valves opening and closing thousands of times per minute under full power conditions. German engineers noted that every cylinder appeared identical, suggesting manufacturing processes capable of producing consistent, interchangeable parts across thousands of engines. This level of manufacturing consistency was becoming increasingly difficult for German industry to achieve as strategic bombing degraded machine tool availability and forced the use of inadequately trained labor, including forced workers from occupied territories who lacked the skills and motivation of pre-war German machinists. The crankshaft represented perhaps the most impressive single component in the entire engine. Forged as a single piece from high-grade steel alloy, the crankshaft measured over 30 inches in length and weighed approximately 200 pounds. It incorporated 9 throws for the 18 pistons, each throw precisely positioned and balanced to minimize vibration at operational speeds, exceeding 2,000 revolutions per minute. The forging required enormous presses capable of shaping white-hot steel under tremendous pressure, followed by precision machining to final dimensions and careful balancing. German engineers recognized the crankshaft as a masterpiece of metallurgy and precision manufacturing. Creating such a component required not just theoretical knowledge of materials and processes, but practical industrial capability at scale. The Americans were producing these crankshafts not as experimental items for prototype engines, but as production components manufactured in quantities sufficient to supply over 125,000 engines by war's end. The supercharger system drew particular attention from German engineers who understood the critical importance of forced induction for maintaining power at altitude. The R-two 800 incorporated a single-stage, 2-speed supercharger directly driven by the engine through a gear train. This supercharger could operate in low blower mode for takeoff and initial climb, then shift to high blower mode for increased boost at altitude, where air density decreased. The supercharger impeller was precision cast from aluminum alloy, with carefully contoured blades designed to compress incoming air efficiently with minimal heating from compression. The entire supercharger assembly was integrated into the presented rear of the engine in a compact installation that demonstrated sophisticated engineering and careful attention to packaging constraints. The system included an intercooler arrangement that cooled compressed air before it entered the cylinders, increasing air density and preventing destructive detonation. But the R-two 800's true performance advantage came not from the engine-driven supercharger alone, but from the turbocharger system that characterized the P-47's installation. Exhaust gases from all 18 cylinders were collected through manifolds and routed through insulated pipes to a turbine unit located behind and below the cockpit. This turbine, spinning at tremendous speed driven by hot exhaust gases, drove a centrifugal compressor that forced additional air into the engine's supercharger. The turbocharger system included automatic regulators that controlled boost pressure and turbine speed without requiring constant pilot intervention beyond setting desired manifold pressure. German engineers understood the theoretical principles perfectly. They had conducted experimental programs exploring similar approaches throughout the 1930s and early war years. But implementing such a system in mass-produced combat aircraft had proven impossible given material shortages and manufacturing limitations that plagued German industry by 1943. The turbocharger required exotic high-temperature alloys for turbine blades that had to withstand extreme temperatures exceeding 1,500 degrees Fahrenheit while spinning at speeds approaching 20,000 revolutions per size. The control system demanded precision manufacturing and reliable components. The extensive ducting needed heat-resistant materials and perfect seals to function efficiently. Every element had to work reliably in combat conditions, exposed to vibration, temperature extremes ranging from -60 degrees Fahrenheit at altitude to over 200 degrees near the exhaust system, and potential battle damage. The Americans had solved all these problems and installed the complete turbocharger system as standard equipment on every P-47 produced. Republic Aviation delivered over 15,000 Thunderbolts during the war, each equipped with a fully functional turbocharger system that operated reliably under operational conditions. This casual implementation of advanced technology as standard production equipment revealed an industrial capacity that German engineers found difficult to fully comprehend. German technical reports from the Rechlin evaluation noted repeatedly that the turbocharger system alone represented a level of engineering sophistication and manufacturing capability that exceeded current German capacity to replicate in production quantities. The materials, the precision manufacturing, the quality control required to produce such systems reliably at scale simply exceeded what German industry could achieve, given strategic material shortages and the progressive degradation of manufacturing standards caused by Allied bombing. The R-2-800's rated power output shocked German engineers who were accustomed to the limitations of German radial engines. At standard military power settings, the engine developed 2,000 horsepower at 2,700 revolutions per minute, using 46 inches of mercury manifold pressure. This represented normal operational power that pilots could use continuously without risking engine damage or reduced reliability. For emergency situations, the engine could utilize war emergency power by injecting a water-methanol mixture into the supercharger, cooling the compressed air charge, and allowing higher boost pressures without detonation. At war emergency power, the R-2-800 produced 2,300 horsepower, an output that exceeded the maximum power of Germany's most powerful operational aircraft engines by over 30%. The BMW 801D produced between 1,700 and 1,730 horsepower at maximum continuous power settings. Germany's most powerful inline engine, the Daimler-Benz DB603, generated 1,750 horsepower in its highest performance variants, and those variants suffered reliability problems that limited their operational use. The American radial engine was delivering substantially more power while demonstrating superior reliability under operational conditions. German engineers conducted detailed analysis of how the R-2-800 achieved such high power output without the chronic reliability problems that plagued German attempts to extract more power from their engines. The investigation revealed a fundamental difference in design philosophy. American engineers had designed the R-2-800 with substantial safety margins built into every critical component. Pistons were sized to handle peak pressures with room to spare. Connecting rods were stronger than strictly necessary for rated power outputs. The crankshaft could handle torque loads exceeding maximum engine output. Bearings were larger and more robust than minimum design requirements suggested. Cooling fins were more extensive than barely adequate heat dissipation demanded. Every component was slightly over-engineered, accepting modest weight penalties in exchange for absolute reliability under the most demanding operational conditions. German design philosophy, constrained by material scarcities that worsened progressively throughout the war, had moved in the opposite direction. German engineers were forced to design to absolute minimums, extracting maximum performance from minimum material quantities. Components were sized precisely to handle expected loads with minimal safety margins. This approach worked acceptably when materials were consistent, manufacturing was precise, and maintenance was thorough. But as material quality declined, manufacturing tolerances opened up, and maintenance suffered from parts shortages and inadequately trained personnel. German engines began failing at increasing rates. The Americans could afford to over-engineer because their industrial capacity allowed it. They had sufficient aluminum, adequate steel, plenty of skilled workers, and functioning machine tools to build engines with generous safety margins without compromising production quantities. The fuel injection system on the R-2-800 represented another area where American engineering exceeded German capabilities. Each cylinder received precisely metered fuel through individual injection nozzles, ensuring optimal mixture ratios across all 18 cylinders under varying power settings and altitude conditions. The system operated mechanically without reliance on electrical components that might fail, using engine-driven pumps and carefully calibrated metering valves. German aircraft engines used various fuel delivery systems, including carburetors on many models and fuel injection on more advanced designs. But German fuel injection systems suffered from increasing quality problems, as precision manufacturing became difficult. Inconsistent fuel delivery between cylinders reduced power output and increased the risk of detonation that could destroy engines in seconds. The American system functioned flawlessly during Rechlin testing, despite thousands of test cell hours and numerous flight test cycles. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The ignition system incorporated dual magnetos, providing complete redundancy. If one magneto failed, the engine continued operating normally on the second magneto, without power loss or increased risk. Each magneto generated electrical current mechanically through rotation, eliminating dependence on external electrical systems. Dual spark plugs in each cylinder, one fired by each magneto, ensured reliable ignition even if individual spark plugs fouled or failed. German engines used similar dual magneto systems, but the quality of German-produced magnetos and spark plugs had declined noticeably by 1943. Magnetos that failed prematurely forced engines to operate on single magneto operation, accepting reduced reliability. Spark plugs that fouled from inferior ceramic insulators caused rough running and power loss. The American ignition components showed no such quality degradation. The lubrication system demonstrated the same attention to reliability and durability evident throughout the engine. A large oil sump held sufficient lubricant for extended operations. Engine-driven oil pumps circulated lubricant under pressure to all bearings, gears, and moving components. Oil coolers reduced lubricant temperature, preventing thermal breakdown that would reduce lubrication effectiveness and cause rapid wear. The system included filters to remove contamination and maintain oil cleanliness. During teardown inspection after test cell operations, German engineers found minimal wear on bearing surfaces, cylinder walls, and other friction points despite extensive running under full power conditions. The lubrication system was clearly adequate for its purpose, protecting engine components effectively even under the severe operating conditions of combat aviation, where engines operated at high power settings for extended periods. German engineers compiled their findings into detailed technical reports that circulated through Luftwaffe technical services and German aviation industry organizations. These reports emphasized repeatedly that the R-2800 represented not just a powerful engine, but a complete manifestation of American industrial philosophy applied to aviation powerplant design and manufacturing. The engine had been designed for absolute reliability under the most demanding operational conditions. It incorporated generous safety margins in every critical component. It used the highest quality materials available without compromise or substitution. It was manufactured to tight tolerances using precision equipment and skilled labor. Most importantly, it was produced in enormous quantities that exceeded German comprehension of what constituted mass production. Pratt and Whitney's main plant in East Hartford, Connecticut, along with production at Ford Motor Company's engine plant and several other facilities, ultimately delivered over 125,000 R-two 800 engines by war's end. This represented more engines of a single advanced type than Germany produced of all combat aircraft engines combined throughout the entire war. BMW produced approximately 61,000 examples of the 801 radial engine across all variants from 1939 through 1945. The Daimler-Benz DB605, Germany's most produced inline engine, reached approximately 42,400 units in total production. Junkers produced approximately 68,000 Jumo 211 engines for bombers and other multi-engine aircraft. Even combining all German production of all engine types, American production of the R-two 800 alone nearly matched Germany's entire output. When American production of other engine types was included, the disparity became overwhelming. Wright Aeronautical produced over 165,000 Rhone 820 Cyclone radial engines. Allison delivered over 70,000 V1710 inline engines. Packard manufactured over 55,000 Merlin engines under license. The numbers documented an industrial capacity that operated on a fundamentally different scale from German capabilities. Individual American engine plants frequently outproduced Germany's entire aviation engine industry. This wasn't a matter of German engineering incompetence or American technical genius. It reflected the vast disparity in industrial resources, manufacturing infrastructure, and access to strategic materials that characterized the American economy versus Germany's increasingly constrained industrial base. The metallurgical analysis of R2-800 components revealed perhaps the most troubling implications for German engineers who understood materials science. The aluminum alloys used throughout the engine incorporated substantial quantities of copper for strength and heat resistance. Germany faced severe copper shortages by 1943, forcing the use of aluminum alloys with reduced copper content and correspondingly reduced mechanical properties. The steel alloys in highly stressed components like the crankshaft, connecting rods, and cylinder barrels incorporated nickel, chromium, and molybdenum in proportions optimized for strength and fatigue resistance. Germany's access to these strategic alloying elements had become severely constrained as the war progressed, and imports from overseas sources were cut off by Allied naval blockade. The high-temperature alloys in the turbocharger turbine blades incorporated cobalt and other exotic elements that provided the necessary properties to withstand exhaust gas temperatures and high rotational speeds. Germany attempted to develop similar alloys, but struggled to obtain sufficient quantities of the necessary raw materials to support production at meaningful scale. American access to these strategic materials reflected the nation's vast domestic mineral resources, supplemented by imports from across the Western Hemisphere and other Allied nations. Copper came from mines in Montana, Arizona, and Chile. Nickel arrived from Canada. Cobalt was sourced from the Belgian Congo through Allied-controlled supply lines. The United States could obtain whatever materials its industry required, without the constraints that progressively strangled German production. The machine tools required to manufacture R2-800 components represented another dimension of American industrial superiority that German engineers understood clearly. Precision boring machines cut cylinder barrels to exact dimensions with surface finishes that minimized friction and wear. Sophisticated lathes machined crankshafts to tolerances measured in thousandths of an inch. Specialized grinding equipment finished bearing surfaces to mirror smoothness. American industry possessed these machine tools in quantities sufficient to support multiple production facilities operating simultaneously. When production demands increased, American factories could acquire additional machine tools from domestic manufacturers who could deliver equipment within months. Germany, by 1943, had lost substantial machine tool capacity to Allied bombing. Remaining equipment was wearing out from intensive use without adequate maintenance or replacement. The machine tool industry itself suffered from the same material and labor shortages, affecting all German manufacturing. Hans-Werner Lerche eventually flew the captured Thunderbolt through a comprehensive test program at Rechlin, exploring the flight envelope systematically according to standard evaluation procedures. His preliminary report contained observations that troubled Luftwaffe headquarters staff who preferred to believe German fighter designs remained fundamentally superior. At altitudes above 25,000 feet, where aerial combat increasingly occurred as Allied bomber formations flew higher to escape German flak, the P-47 Thunderbolt was not inferior to German fighters. It was superior in specific crucial ways that negated German advantages in maneuverability and rate of climb at lower altitudes. The turbocharger gave the R2-800 full-rated power at altitudes where German engines were gasping for air and delivering perhaps 70% of sea-level output. The power advantage translated directly into superior speed, better climb rate, and enhanced maneuverability at the altitudes that mattered strategically. German pilots, fighting at 25,000 feet or above, faced opponents whose engines were producing 500 to 600 more horsepower than their own. That power differential was insurmountable through pilot skill or tactical cleverness. But Lerche's flight testing report represented only one component of the intelligence gathered from captured Thunderbolts. The engine examination provided insights that extended far beyond the tactical aviation questions of how to fight the P-47 combat. German engineers recognized that the R2-800 revealed fundamental truths about comparative industrial capabilities that had profound strategic implications. The Americans had designed an engine that prioritized absolute reliability and maximum power over elegant efficiency or resource conservation. They had manufactured it using the best available materials without compromise. They had produced it in quantities that suggested industrial capacity operating without meaningful constraints. Most troubling, they had done all this while simultaneously producing numerous other advanced engine types for fighters, bombers, and transport aircraft. German engineers compiled recommendations based on their evaluation of captured American engines. These recommendations emphasized the urgent need for Germany to develop more powerful engines if any hope remained of competing effectively in the air war. They noted the critical importance of improving German access to strategic alloying materials. They stressed the necessity of enhancing quality control in manufacturing, as standards had degraded noticeably. But these recommendations, however professionally prepared and technically sound, could not address the fundamental problem. Germany, in 1943 and beyond, simply lacked the industrial resources, the strategic materials, and the manufacturing infrastructure to implement what American industry treated as standard practice. Understanding American capabilities did not grant Germany the aluminum, copper, nickel, chromium, molybdenum, and cobalt needed to replicate American metallurgy. Recognizing the importance of precision manufacturing did not provide the machine tools, skilled workers, and consistent electrical power supply necessary to achieve American production tolerances. Comprehending the value of generous engineering safety margins did not eliminate the resource constraints that forced German designers to optimize every component to absolute minimums. The captured R-two 800 engines served as tangible physical evidence that American industrial capacity operated on a scale Germany could not match. Every bolt, every forged component, every precisely machined surface told the same story. The Americans had access to effectively unlimited resources relative to German industrial capacity. They had functioning supply chains that delivered whatever materials their factories required. They had skilled workers who could execute precision manufacturing consistently. They had electrical power, machine tools, and transportation infrastructure that continued operating despite the war. By comparison, Germany's industrial situation deteriorated progressively throughout 1943 and beyond. Allied strategic bombing destroyed factories, power plants, and transportation infrastructure faster than they could be repaired or replaced. The loss of Romanian oil fields in August of 1944 eliminated Germany's primary source of natural petroleum, forcing greater reliance on expensive synthetic fuel production that required enormous inputs of coal and electrical power. The forced conscription of skilled workers into military service replaced experienced machinists with inadequately trained forced labor from occupied territories. These workers lacked the skills, experience, and often the motivation to maintain pre-war quality standards. The progressive degradation of component quality became evident in German aircraft engines that suffered increasing failure rates as the war continued. Strategic material shortages worsened continuously. Copper allocations to aviation engine manufacturing were reduced repeatedly as the metal became scarcer. Nickel and other strategic alloying elements became virtually unavailable by 1944, forcing the use of inferior substitute materials. The high-temperature alloys needed for turbo-supercharger development remained beyond German production capability throughout the war. German engineers recognized the implications with uncomfortable clarity. They were attempting to compete industrially against an opponent whose combined industrial capacity, when American, British, and Soviet production were combined, exceeded German capacity by factors of 5 or more. The disparity wasn't subtle or marginal, it was overwhelming and decisive. The examination of captured R-two 800 engines provided German engineers with detailed technical intelligence about American engine design, materials, and manufacturing processes. This intelligence was professionally gathered, carefully analyzed, and thoroughly documented in technical reports that circulated widely through German aviation organizations. But intelligence alone could not produce the resources needed to close the gap. Additional captured P-47 seconds provided further opportunities for German evaluation. On May 29, 1944, Another Thunderbolt landed in German hands when Second Lieutenant Lloyd S. Hathcock of the 302nd Fighter Squadron became disoriented during a ferry flight and mistakenly landed at enemy-held Rome Littorio airfield in Italy. His aircraft was quickly seized and transferred to Rechlin, where it eventually received the designation T9+LK within the Zircus Rosarius Evaluation Unit. Each captured example provided additional data points, confirming what German engineers had learned from earlier examples. The engines were consistently high quality across multiple examples. Manufacturing standards remained constant. No evidence of material substitution or quality degradation appeared even in later production aircraft. The Americans were maintaining production standards even as their output increased to levels German industry could scarcely imagine. The captured Thunderbolts were eventually transferred to the Sonderstaffel Rosarius, the special Luftwaffe demonstration unit that traveled to frontline fighter bases throughout occupied Europe. German pilots could see captured Allied aircraft firsthand, learn recognition features, and understand combat characteristics. The demonstrations served dual purposes, both educational and psychological. But when German pilots saw the massive radial engine that powered the Thunderbolt, many recognized they were viewing technology their own industry could not replicate. The Tu-800 represented not just superior engineering, but superior access to resources, superior manufacturing capability, and superior industrial organization operating at national scale. Post-war interviews with Luftwaffe pilots and engineers who examined captured American equipment revealed the psychological impact of confronting evidence that American industrial capabilities exceeded German achievements in critical areas. Official propaganda had consistently portrayed American industry as capable of mass production, but fundamentally inferior in engineering sophistication and technical excellence. The R-800 challenged that comfortable narrative directly. This was not crude equipment mass-produced without attention to quality. It was sophisticated engineering executed flawlessly in enormous quantities, using manufacturing processes that maintained consistent quality across thousands of examples. The engine demonstrated that American industry could achieve both quantity and quality simultaneously, a combination Germany found increasingly impossible to maintain. The strategic implications extended beyond aviation to broader questions about the war's likely outcome. If American industry could design and produce aircraft engines of this sophistication in these quantities, while simultaneously producing everything else a modern military required, how could Germany hope to compete? The question troubled German military planners and political leaders who recognized that industrial capacity had become the decisive factor in modern warfare. Germany had entered the war with arguably the world's most advanced military, equipped with weapons that were generally superior to their opponents on a one-to-one basis. German soldiers, sailors, and airmen were superbly trained. German tactics were more refined than most opponents initially. German operational art and strategic planning had proven devastatingly effective in the early war years. But German industry fundamentally lacked the capacity to sustain these initial advantages when facing opponents with vastly greater industrial resources. American aircraft production doubled repeatedly. 1940 saw 3,500 aircraft delivered. 1941 brought 12,500. 1942 delivered 47,800. By 1944, American factories were producing 96,000 aircraft annually. Germany never exceeded 40,000 aircraft in any year, despite desperate efforts to increase production. The disparity widened every year as American production expanded, while German output stagnated or declined due to bombing damage, material shortages, and labor constraints. The quality gap between American and German aircraft also widened rather than narrowing. In 1942, German aircraft were often superior to American types. By 1944, American aircraft equaled or exceeded German designs in virtually every important category. By 1945, the gap had become a chasm. American fighters like the P-47 Newtons and P-51H represented evolutionary refinement of already excellent basic designs. German fighters like the Ta-152 represented desperate attempts to extract more performance from industrial systems, collapsing under the combined weight of strategic bombing, raw material shortages, and the replacement of skilled workers with poorly trained forced labor. The R-two 800 engine became a symbol of this industrial disparity to German engineers who examined it in detail. They could measure every dimension precisely. They could analyze material composition through metallurgical testing. They could document manufacturing techniques through careful observation. They could compile comprehensive technical reports describing exactly how the Americans had achieved such remarkable performance and reliability. But all this knowledge could not conjure the aluminum Germany needed. Understanding American metallurgy did not grant access to copper, nickel, chromium, and molybdenum in sufficient quantities. Recognizing the importance of precision manufacturing did not repair bomb-damaged factories or replace worn-out machine tools. Comprehending American quality control standards did not restore the skilled workforce that had been conscripted into military service or killed in Allied bombing raids. The psychological impact on German engineers who thoroughly understood the magnitude of industrial disparity they faced cannot be overstated. These were highly educated, professionally competent men who had dedicated their careers to advancing German aviation technology. They understood engineering principles as well as their American counterparts. In many areas of theoretical knowledge, German engineering education was arguably superior to American equivalents. But theory alone could not build engines. Knowledge could not substitute for resources. Understanding could not overcome industrial capacity operating at fundamentally different scales. German engineers found themselves in the position of understanding exactly why they were losing the industrial war while being powerless to change the outcome. The R-two 800's reliability under operational conditions proved as significant as its raw power output. American maintenance records showed that properly maintained engines routinely operated for hundreds of hours between overhauls. Engine failures remained rare enough to be noteworthy events rather than routine occurrences. When engines did require maintenance, the robust construction and generous safety margins meant that problems could often be addressed through component replacement rather than complete engine replacement. German engines, by contrast, suffered increasing reliability problems as the war progressed and manufacturing quality degraded. The BMW 801, which had been reasonably reliable in early production, developed a reputation for oil system failures, cylinder cracking, and bearing failures in later variants. The problems stemmed directly from material quality degradation and manufacturing tolerance issues, caused by the factors German engineers understood but could not control. Pilots flying aircraft with unreliable engines faced additional stress beyond the normal dangers of combat operations. An engine failure over enemy territory meant certain capture or death. Engine failures during combat maneuvering often proved fatal, as pilots lacked altitude or time to bail out successfully. The knowledge that their engines were less reliable than American equivalents added to the psychological burden German pilots carried into every mission. The captured R-two 800 engines eventually provided components for keeping test aircraft operational as long as possible. When original engines required maintenance or suffered damage during testing, German technicians cannibalized parts from multiple captured engines to maintain one or two flying examples. This practice reflected German resourcefulness in maintaining evaluation aircraft, despite lacking access to genuine spare parts or technical support from American manufacturers. But the cannibalization practice also highlighted the fundamental difference in logistical support between American and German aviation. American P-47 squadrons received regular shipments of spare engines, replacement parts, and consumable supplies. When an engine reached its overhaul interval or suffered damage, mechanics simply replaced it with a fresh engine from supply stocks. The removed engine was sent to depot-level maintenance facilities for overhaul and eventual return to service. German fighter units struggled with chronic spare parts shortages that worsened progressively throughout 1944 and 45. Engines that required overhaul often couldn't be replaced because no spare engines were available. Mechanics improvised repairs using whatever materials they could obtain, accepting reduced performance and reliability as inevitable compromises. Aircraft sat grounded awaiting parts that never arrived while pilots stood idle despite desperate need for fighter sorties. The logistical disparity reflected broader differences in industrial organization and resource availability. American industry produced spare parts in quantities that ensured units could maintain high operational readiness rates. German industry focused production capacity on complete aircraft rather than spare parts, reasoning that new aircraft were more valuable than maintaining old ones. But this strategy failed when combat attrition exceeded production and aging aircraft couldn't be maintained for lack of basic components. The technological intelligence gathered from R-two 800 examination informed several German engine development programs during 1944 and 45. Engineers attempted to incorporate lessons learned into improved versions of existing engines and into new designs intended to restore German competitiveness. The BMW 801 received various modifications aimed at improving reliability and increasing power output. Daimler-Benz worked on advanced versions of the DB605 with larger displacement and higher boost pressures. Junkers developed the Jumo 213, an inverted V12 engine designed to produce over 2,000 horsepower. These programs reflected German recognition that their existing engines were inadequate for the missions German fighters were being asked to perform. But development programs required time, resources, and testing that Germany could not provide in sufficient quantities. Prototype engines showed promise in limited testing, then revealed serious problems when pushed to full development. Manufacturing the new engines in quantity proved impossible given material shortages and factory capacity constraints. Most advanced engine programs never progressed beyond prototype stage before the war ended. The most successful German response to Allied air superiority came not from improved piston engines, but from revolutionary jet propulsion. The Messerschmitt Me 262, powered by Junkers Jumo 004 turbojet engines, entered limited operational service during 1944. The aircraft possessed dramatic speed advantages over Allied piston fighters and could devastate bomber formations when flown by skilled pilots. But the Me 262 suffered from severe limitations that prevented it from decisively influencing the air war. The Jumo 004 engines were notoriously unreliable, requiring complete replacement after just 10 to 25 hours of operation. The engines consumed vast quantities of aviation fuel that was increasingly scarce. The aircraft required extensive concrete runways that were vulnerable to Allied attack. Training pilots to fly jets required time and fuel Germany could not spare. Most critically, the Me 262 arrived too late and in too few numbers to matter strategically. Total production reached approximately 1,400 aircraft, but only a fraction ever became operationally ready. The type scored notable successes against Allied bombers, but could not prevent the systematic destruction of German industry and infrastructure that sealed Germany's fate. The examination of captured American engines revealed to German engineers that their opponents had solved the practical problems of producing reliable, powerful aircraft engines at industrial scale. This wasn't theoretical knowledge or laboratory achievements. American factories were delivering production engines that worked reliably under the most demanding operational conditions, and they were producing these engines in quantities that enabled American air forces to dominate the skies over Europe. By the war's end, P-47 Thunderbolts had flown over 546,000 combat sorties in the European theatre alone. The type destroyed approximately 3,752 enemy aircraft in aerial combat, while suffering roughly 3,499 P-47 seconds lost to all causes. This exchange rate appears modest until one considers that Thunderbolts served primarily in ground attack roles from mid-1944 onward, facing intense anti-aircraft fire during low-altitude missions rather than engaging primarily in air-to-air combat. In the fighter escort role during 1943 and early 44, before P-51 Mustangs took over long-range escort duties, P-47 seconds achieved favorable exchange rates against German fighters, particularly at high altitudes where the turbocharger provided decisive advantages. The rugged R-two 800 engine proved ideal for dangerous ground attack missions, where reliability and damage tolerance mattered more than ultimate performance. Thunderbolt pilots flying ground attack missions destroyed staggering quantities of German equipment according to official claims documented through camera footage. Over 86,000 railway cars, 9,000 locomotives, 6,000 armoured fighting vehicles, and 68,000 trucks were destroyed or damaged by P-47 seconds. While such claims inevitably included some duplication and overcounting, the scale of destruction was undeniable and measurably impacted German military operations. The deep rumble of Pratt and Whitney R-two, 800 engines at low altitude, became a sound German ground forces learned to fear. The psychological impact of constant air attack, combined with substantial material losses and disruption of logistics, degraded German combat effectiveness throughout the final year of the war. German troops could rarely move during daylight hours without risking air attack. The fate of William Roach's P-47D, the aircraft designated T9+FK by German evaluation units, provides an epilogue to this story. The aircraft survived the war and was recovered by American forces at Göttingen in May of 1945. American intelligence teams photographed it among a collection of captured Allied aircraft the Germans had been evaluating. The aircraft was eventually scrapped rather than preserved for historical purposes. Lieutenant Roach spent the remainder of the war at Stalag Luft 1 near Bath, Germany. He was liberated by Soviet forces in May of 1945 and returned to the United States, having survived 20 months of captivity. The engine from his aircraft, after being thoroughly examined, measured, photographed, and tested by German engineers, had taught lessons that arrived too late to influence the war's outcome. Hans-Werner Lersch survived the war despite flying 125 different aircraft types throughout the conflict, including numerous captured Allied aircraft. His remarkable safety record, never crashing or seriously damaging a single aircraft during his test pilot career, stands unique in aviation history. After the war, he provided extensive debriefings to Allied intelligence services about German aircraft development programs and captured aircraft evaluation procedures. His memoirs, published first in German during 1977 and translated into English in 1980, provide detailed first-hand accounts of German evaluation programs. His professional observations about captured American aircraft, including his frank assessments of areas where Allied designs exceeded German equivalents, offer valuable insights into how Luftwaffe technical services understood their opponents' capabilities. The broader lesson that emerges from German examination of captured R-two 800 engines transcends specific technical details. The engine evaluation at Rechlin demonstrated that by 1943, the outcome of the air war over Europe was being determined not by pilot skill, tactical innovation, or even individual aircraft performance, but by industrial capacity applied at national scale. The nation that could design adequate equipment and produce it in overwhelming quantities, while simultaneously manufacturing everything else a modern military required, would inevitably defeat opponents who produced technically superior equipment in insufficient quantities. Germany's strategic situation by late 1943 placed them in competition against opponents whose combined industrial capacity exceeded German capability by factors of 5 or more. When Britain refused to capitulate after France fell, when the Soviet Union survived the initial German onslaught and relocated industry beyond German reach, and when the United States entered the war with its vast, untouched industrial base, Germany's path to military victory effectively closed. The only remaining question was how long Germany could continue fighting and how much destruction would occur before inevitable defeat. The story of captured R-two 800 engines at Rechlin thus becomes a microcosm of Germany's broader strategic dilemma. German engineers could examine American equipment, understand American capabilities, and accurately assess American industrial strength. This knowledge was professionally gathered, carefully analyzed, and thoroughly documented in technical reports distributed through appropriate channels. But knowledge alone could not produce the aluminum, steel, copper, nickel, chromium, cobalt, machine tools, skilled workers, undamaged factories, functioning power grids, and intact transportation networks required to compete with American industrial output. The Pratt and Whitney R-two 800, examined in minute detail by German engineers at Rechlin, proved a final truth about industrialized warfare in the 20th century. Material abundance systematically applied through competent engineering and adequate tactical execution would defeat technical excellence constrained by resource scarcity. The most powerful element in America's arsenal was not any individual technology, however impressive, but rather the complete industrial system that could conceive, design, develop, test, produce, and logistically support thousands of complex weapons systems simultaneously while maintaining quality and continuously improving designs based on combat experience. The captured engines taught this lesson with undeniable clarity. German engineers measured it precisely, documented it professionally, and reported it accurately through their chain of command. The lesson arrived too late to matter strategically. By the time William Roach's Thunderbolt was being meticulously examined at Rechlin in late 1943, the war's outcome was already determined by industrial mathematics that no amount of German engineering skill or pilot courage could overcome. The R-two 800 engines sitting in German test facilities, their components spread across examination tables, their performance characteristics thoroughly documented in technical reports, represented a future that had already arrived. A future in which industrial capacity had become the decisive factor in modern warfare, where access to resources mattered more than theoretical knowledge, and where the ability to mass-produce sophisticated equipment reliably determined victory, more surely than any tactical brilliance or individual heroism could achieve. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.